Okay, so consider this hoop with two forces acting on it, causing a rotation around point C. First, I just want to know what is the net torque. See, I'll call this torque 1, and I'll call this torque 2. Now, torque 1 causes a counterclockwise motion, so it's negative, and torque 2 causes a clockwise motion, so it's going to be positive. So for part A, the net torque is going to be the sum of those, negative torque 1 plus torque 2. Torque 1 is going to be F times R times sine of theta. That's 40 times this distance, which is 2 meters. So 40 newtons, 2 meters. The sine of 90 is equal to 1. So I'm just going to leave off that sine of theta. Here I have 20 newtons times 2 meters times the sine of 30. And so that's negative 80, 40 plus 20, that's equal to negative 60 Newton meters. So that's part A. For part B, I want to know what is the speed after 3 seconds. So I have to do several steps here. First, I need to find the moment of inertia. If I look at my equation sheet for a hoop, the moment of inertia is mr squared. It has a mass of 4 kilograms and a radius of 2 meters. Next, I can use that to find alpha. Since I know that torque is equal to I times alpha, alpha is equal to the torque divided by the moment of inertia. That's 60 divided by 16. That's in radians per second squared. Now finally, I can find omega, which is omega naught plus alpha t. This is 0 because it's initially at rest. It's equal to 3.75 times our time, which was 3 seconds. It's 11 radians per second. Keeping 2 sig figs there because that's what the smallest number of sig figs I had. So net torque is minus 60, and then omega is 11, but then you also had to find these two things en route. Hollow sphere has a mass of 4 kilograms and a radius of 2 meters. It rolls with a linear speed of 2 meters per second. Here I want to know what is the angular speed of the sphere, what is the total energy of the sphere, and then what is the displacement for it to come to rest. First of all, this is a hollow sphere, so I'm going to calculate I up here for a hollow sphere. That's 2/3 mr squared. That's going to be 2/3 of the mass, which is 4 times 2 meters squared. That's 8 times 4 is, what's 8 times 4? 32 divided by 3. 10.7. Let's see, I will just call that 11 kilogram meters squared. Okay, so now for part A, I want to know what is the angular speed of the sphere. Well, look, I'm given the linear speed, that's v, and so I know that v is equal to omega times r. So if I want to know omega, that's just going to be v divided by r, which is going to be 2 meters per second divided by the radius of 2 meters. So it has an angular speed of 1 radian per second. It should be 1.0. For B, what is the total energy of the sphere? So this thing has a linear speed, but then it also has a rotational speed. So the kinetic energy is going to equal to the linear, or translational, 1/2 mv squared, plus the rotational, 1/2 I omega squared. Now we have everything here that we need, so we'll just plug those things in. I have 1/2 of the mass, which is 4 kilograms, times the speed, which is 2 meters per second. That squared plus 1/2 of 11 times omega, which I found to be 1 radian per second. That squared, that's 2 times 4, that's 8 joules plus 5.5 joules. This should be 8.0 joules. So that gives me, what's that? 8 plus 5 is 13. 14 joules. So that's the total energy. There's omega. And then I apply a force that's 10 newtons tangentially to the surface of the sphere. And I want to know the angular displacement. Now remember that the work, previously we said that that was force times displacement, but when applied in a rotational frame, it's going to be equal to the torque times the displacement. Now, all this work has to cause a change in energy, and that change in energy will be that 14 joules. So I'll say that 14 joules is equal to the torque times the angular displacement. I can find that torque is just equal to Fr sine theta. Uh, that's 10 newtons times the radius, which was 2 meters. So that's 20 Newton meters. Sorry. So I have 14 divided by 20 is equal to theta, and that's going to be what 7 divided by 10.7 radians. So that's our answer for theta. Now number 3, I have a disk that's rotating with an angular speed, so omega is 3 radians per second. And then I have a second object with a 2 kilogram mass on the outer edge of the spinning disk. So I want to know first, what is the angular momentum of the disk? So for part A, well, before I find the angular momentum, I need to find the moment of inertia. For a cylinder, that's going to be 1/2 mr squared. That's 1/2 of 4 kilograms times 2 meters squared. That's 2 times 4, that's 8.0. Yeah, 8.0 kilogram meters squared. That's the moment of inertia. Now to find the angular momentum is going to be L equals I times omega. That's going to be 8 kilogram meters squared times omega, which is 3 radians per second. So I get a moment of an angular momentum, excuse me, of 24 kilogram meters squared per second. So that is my moment, or my angular momentum of 24. Now for part B, I want to know what is the total moment of inertia of the disk and the object. So I'm placing an object here at a radius of 2 meters, and that object has a mass of 2 kilograms. And we're going to treat that as just a discrete particle. The total moment of inertia will equal to the moment of inertia of the disk plus the moment of inertia of the particle. That's going to be 1/2 mr squared. We've already found that, right? It's 8 plus mr squared. And so that's going to be 8 kilogram meter squared plus the mass of the particle, which was 2 kilograms, times the radius, which is 2 meters squared. So that's 8 plus 8 are 16 kilogram meters squared. So my new moment of inertia is 16 kilogram meters squared. Notice my moment of inertia went from 8 up to 16, so it's doubled. And now I want to know, what is the new angular speed? Well, you could probably say, well, since the moment of inertia is doubling, that means that the speed is halving. And so the final speed of this thing is going to be, let's see, initially it was 3 radians per second, so now it's going to be 1.5 radians per second. You might be able to just sort of reason that out because our moment of inertia is doubling, so you know it's going to slow down. But if not, I can say Li is equal to Lf. I know that momentum is always conserved. Li I've already found, that's 24 kilogram meters squared per second. And then that's going to equal to I final omega final. So 24 is equal to 16 times omega final, and then I find that omega final is equal to 1.5 radians per second. That's the right answer. Okay, look at the multiple choice. Drum majors carry a mace that's 2 meters long, has a mass of 1 kilogram. Spins the mace about the mace's midpoint with an angular velocity of 6 radians per second. And then he throws it up continues to spin. He throws it up in the air to a height of 2 meters, and it continues to spin at the same rate. What is the energy of the mace? So this is really similar to the problem we did before, except now the total energy is equal to the uh, kinetic energy rotational plus the potential energy that it has at this certain height. So that's going to be 1/2 I omega squared plus mgh. Let's find I first. If I look on my table for a thin rod of length b rotating end over end, that's going to be 1/12 mb squared. 1/12 of the mass, which is 1 kilogram, times b, that's the length, so it's going to be 2 meters squared, so that's 4 over 12, or 0.33. So I'll just call it 1/3. So it's going to be 1/2 of the moment of inertia, which is 1/3 kilogram meter squared, times the angular speed, which is 6 radians per second, that squared, plus the mass, which is 1 kilogram times 10, that's g, times h, it goes up to a height of 2 meters, that's h right there. So now I have 6 plus 20 equals 26 joules. So B is the right answer. Figure skater is spinning with her arms extended. And then she pulls her arms inward and she continues to spin. Well, I know that a couple things are going to happen. As she pulls her arms inward, her moment of inertia is going to go down and her omega is going to go up. But I know that the total angular momentum has to remain the same. So first I can just get rid of these here, here, and here, that my angular momentum has to remain the same because there are no external forces acting on it, no external torques. But what happens to the energy? Well, because the energy is equal to 1/2 I omega squared, let's say that this goes down by a factor of half and say this doubles. Well, if I have a factor of a half here and I have a factor of 2 here, that gives me a 4.5. So I'd have twice the kinetic energy. So while that angular momentum remains the same, the energy increases. All right, rank the moments of inertia. This was relatively easy because, I have the one that has the most mass is this point, and then they go in. Let me repeat that. So the one that has the most mass at biggest radii is point D. And then the second most mass at the biggest radii is C, and then B, and then A. So D is the biggest. Okay, there we go. B is the right answer for number 3. All right. This figure shows an arrangement of 3 particles rotating about a common axis. What is moment of inertia? So I is the sum of mr squared. That's going to be 2 kilograms times 0 squared. So of course that moment of inertia doesn't count. 5 kilograms times 2 meters squared plus 4 kilograms times 3 meters squared equals 20 plus 36 equals 56. D. 2 bars of identical dimensions and mass are spinning about a central axis. First is spinning at 4 in the clockwise direction. The second spin is at 8 in the counterclockwise. Okay, 2 bars engage with one another and begin spinning the same angular velocity. So I know that Li equals Lf. I also know that these two have identical dimensions and mass, so I1 is equal to I2, both of those particles. This is going to be L1 plus L2 initial will equal to L1 plus L2 final. Those two have to remain the same. So I can have L1 is going to be I'm just going to call it I because they're both the same, times 4 revolutions per second, but it's going to be negative, plus I times 8 revolutions per second, which is positive because it's, counterclockwise, isn't it? Yeah, counterclockwise. And then they engage with one another. That means that the total moment of inertia is going to be 2I. These two bars come together. And I want to know what is omega final. Well, notice here, I don't know I, but these all cancel out. So I get 4 equals 2 omega f. So omega f is equal to 2 revolutions per second. Notice that the units don't have to be in SI form. They can be in revolutions per second, but they will all cancel, or not cancel out, but they'll all remain consistent. All right, this bar has 3 forces on it. What is the angular acceleration of the bar? Well, first of all, let's just find um, the moments of inertia. We've already seen a bar. It's 1/12 mv squared. Look on your equation sheet to get that. That's 1/12 of 2 kilograms times the length, which is 6 meters. That's squared. 2 times 36, 72, 12, 6 kilogram meter squared. Yeah, of course, 6. Okay, so that's the moment of inertia. Now I find the net torque, but look, made this one really easy, right? Because this one, the torque that it causes is 0 because it's at the axis of rotation. This one, its torque is 0 because theta is equal to 180 degrees or 0 degrees. But that doesn't provide any torque at all. So it's really only this force, and it causes a torque of 2 newtons times 3 meters or 6 Newton meters. And now, if I want to know alpha, that's just torque divided by I, r6/6, which is equal to 1 radian per second squared. So C is the right answer. These 4 wrenches have forces of the same magnitude applied to them. They're at different angles, but the same magnitude of force and at different moments of inertia, or excuse me, lever arms at different lever arms. I want to know which has the greatest torque, which has the least torque. Well, the one with the greatest torque is going to be the one at the biggest um, lever arm, moment arm, with the least angle, with the angle closest to 90 degrees. So that would be this one. And then the one with the smallest torque will be the one at the shortest moment arm with the biggest angle. So that would be this one. So 3 and then 4. Oh, there we go. B is the right answer. A beaker is filled with water and you drop a steel block into the beaker as in this figure. Some of the water spills over the edge. Which of these relationships best describes the mass of the block and the mass of the spilled water? The mass of the block is going to be bigger than the mass of the water. That the block is more dense than water. The buoyant force is not enough to support the block. Now, keep in mind that if I had an object that was floating, in that case, the buoyant force would be equal to the weight of the object, and the buoyant force is equal to the weight of the displaced fluid. So in that case, if it were floating, then the mass of the block would equal the mass of the water. But that's not the situation that I have. I have a block that is sunk to the bottom. A rectangular boat is 2 by 1 meters. To what depth is the boat submerged if it has a mass of 500 kilograms? Well, here's my boat. I have a weight, a buoyant force. I know that as it's floating, those two are equal. The buoyant force is rho vg, and the weight is m times g. Um, the g's cancel. The volume that is displaced is equal to the mass of the boat times the density of water. So that's going to be 500 kilograms over 1,000. That's the density of water. That's in your data table if you don't know it. So that's 0.5 cubic meters. So that's my volume, but I need to know what now is the depth. I know that volume is length times width times height. and that's equal to 0.5. That's going to be 2 by 1 and h, which is 0.5. That means that h is equal to 0.5 divided by 2, or 0.25 meters. A is our answer. In the flow of an ideal fluid, what happens if the velocity of the fluid increases? As the velocity goes up, the pressure goes down. That's from Bernoulli's principle. Water flows through a pipe at 3 meters per second with cross-sectional area of 0.5 meters squared. The pipe grows wider. All right, so my area here is 0.5 square meters. My velocity is 3 meters per second. Here my area is 1 square meter. I mean, you probably know that this is going to go slower, so I can get rid of A and C, and it's going to go slower by a factor of 2. So this velocity, I want to know what it is. I say A1V1 equals A2V2. So let me step back. Because the area got bigger by a factor of 2, I know that the speed has to get smaller by a factor of 2. You probably know that if you've been doing these. But if not, this is how you do it. You take the equation of continuity. So it's 0.5 square meters times 3 meters per second is equal to 1 square meter times V2. And you solve that for V2, and we find that V2 is equal to 1.5. Blood enters a clogged artery, as in this figure. What happens to the pressure of the blood inside the clogged portion of the artery? Well, here, the velocity is going to go up. That means the pressure is going to go down. The aluminum block has a mass of 1,200 kilograms. What is its volume? Well, no, density is mass over volume. So volume is mass over density. That's 1,200. So look up the density of aluminum. It's in your table. It's 2,700. That's about a half. Must be 0.44. Following is a diagram for a hydraulic jack. The piston on the left is A1, piston on the right is A2, have an input force of 20 newtons. So this is 0.5 centimeters squared. This is 20 newtons. This is 1 centimeter squared. And I want to know what force is put out there. I know that pressure on one side is equal to the pressure on the other side. That's F1 over A1 equals F2 over A2. My pressure goes up by a factor of 2, so my force is also going to go up by a factor of 2. So you might know just from that relationship that the answer has to be C. I mean, in this hydraulic jack, I get a bigger force out on the side with the bigger piston. But if you don't remember that, we can just go with this definition from Pascal's principle. This is Pascal's principle, by the way. And say F1, that's 20 over 0.5 is equal to F2 over A2, which is 1. Solve that for F2. It's going to be equal to that, 40. Pascal's principle. Is this one. Now you might think that this is the one, but you can have a hydraulic jack that is different, where that would not be the case, where this one is your input force, and this one is your output force. And in this case, your F out would actually be smaller than your F in. So that's why D is not the right answer. This is Archimedes' principle, and this is Bernoulli's principle. Right, which statement best describes the relationship between P and P naught? Well, these are at the same level, so they're equal to one another. What is the height of the pressure when P is equal to 1 atmosphere? This is water. We've talked about this, so you might remember that the answer is that. But if not, we can say that P1 is equal to P2 plus rho GH. But this is a barometer, so P2 is equal to 0. So P1 is 1 atmosphere, so that's 1 times 10 to the 5th pascals. And that's equal to the density of water, which is 1,000, times the G, which is 10, times H. And so I do that, and I get H equals 10 meters. All fluids are gaseous. gases or liquids. There are some metallic fluids, but that's not it. All fluids are liquids. That's not true. All liquids are fluids, but not all fluids are liquids because some liquids are gases. Not all fluids, of course, are transparent. All right, copper wire of length. Let's just write down what we know here. This is L naught equals 2.0 meters. The area is 7.1 times 10 to the minus 6 square meters. Look, I made everything in SI units for you, so it makes this a lot easier. What is the increase? Delta L. I want to know that. I need to know the Young's modulus, but this is copper wire, so it's 11 times 10 to the 10th. So remember from our equation sheet that our stress is equal to our strain times the Young's modulus. And then I'm going to solve, just do delta L, L naught. So now we solve this for, what am I looking for, delta L, and that's going to be F L naught over YA. So I'll put those numbers in. L naught times 2, making sure I get my parentheses. I get 0.005 meters. Of course, that's not an option. Oh, but then I realize that this is in millimeters. So that means I need to move that decimal place over 3 spots. I get 5 millimeters. And of course, the answer here is me. Although these are some really great students. These are all chemistry alumni. Crystal Verrett, she's a chemist, I think at Shell, if I'm not mistaken. She also runs like a dance company or something. It's kind of cool. Devin Bourgeois is a doctor. He's a doctor over at the Family Doctor Clinic. Jackie Ponville is a researcher. She was at MD Anderson, but now she's at AstraZeneca. She just moved to AstraZeneca. And Shane Swan is a industrial chemist at oh gosh, SGS, I think. He ran for state senate last year. He didn't win, unfortunately. I think he would have been really great, um, but you know, all of you are my favorites. So. All right, good job.